For our BJT bias circuit shown, we're asked what value of RC in kiloohms is needed to allow the maximum possible peak to peak. So important parts here is the RC that we're finding, and then this part right here to allow the maximum possible peak to peak signal swing on the collector without clipping. When we're given values, we can assume the transistor is in the forward active region. That's another important part right here. The base collector junction cannot be forward biased as well. And we're going to neglect the effects of base width modulation. So we can start solving for this. Now, this is going to be very similar to the previous problem that we've looked at. And that one, it can be found in the playlist link below the like button, but it'll look like this. Now, our circuit is just a little bit different. This is an NPN. Now we're solving for a PNP. So there are going to be some similarities. And the first similarity is that IB cannot equal to 0. And since it cannot equal 0 for a BJT, we need to create a Thevenin's equivalent circuit for the base bias circuit. So we can do this. It's going to be the same process as last time. Not exactly the same because obviously our currents are going in different directions. So we're going to start this with the node up here, which is our plus VCC, and then it's going to go down into our RE, and then it's going to go into our VE right here, and then after our VB we are going to go into our PNP. So it's going to look like this, and then we can go down here. We're going to have our base emitter, but we'll draw that in a second, our VB, and then we are going to have our Q. We of course have our VC, we have our RC, and then this is all going to ground. Now, this is the same thing that we looked at last time, where here we are going to want our VBB. So that's what's going to happen right here. And then we're going to connect this to this right here. Now we're going to have some resistance across this, and this resistance is our RB1 and RB2 in parallel, and we're going to call this RBB. So that's what that's going to look like. Now we have some currents. We have our IE, we have our IB, and we have our IC. So those are not going to change. That's the equivalent circuit. Now, we know what we want to find, right? We want to find our RC. So let's start this out with that. First thing that we're looking for, RC, we can set it equal to. Well, our RC here is going to be a little bit different than last time. Last time we looked at the top part right here, but now it's in the bottom part. So our RC for this is going to be the source voltage over our RC, which is VC, minus the other voltage, which here is just ground. So it's going to be minus 0 over our IC. Now that that's done, we can really just rewrite this as VC over IC. But we don't know our VC, nor do we know our IC. So we're gonna need to solve for this. Now, I've copied this over from a previous problem. It's to maximize the output swing of the collector without clipping. We bias our VC, which is what we want here, halfway between its max and min values. So here, though, we're going to be changing this. So the max value would be the VB going into our VC, and our minimum value would just be the 0 volts. So the way we would solve this is we would just take our VB, and then we would divide it by 2. That way we get half of this. So I'm also going to put this here as well, and we can keep that in mind. So we can rewrite this as our VB over 2 times our IC. But now, of course, we want to solve for our IC now. If we look at the notes that are linked below the like button, for IC, there's a few different ways we can solve for it. And we're going to use the way where you have our IC is equal to our alpha times IE, because we could say that our IE times the beta over beta plus 1 if we substitute this in for our alpha. Now we need to solve for our IE now, because we know our betas. Our beta here is given as 20, a pretty low value. So step 3 is going to be solving for our IE. Well, for our IE, what we're going to want to do is we're going to write a expression around the voltage base emitter loop. And that's going to be like this part right here. So we have our, and we're not going to be solving explicitly for our IE here, we need to write an equation for it. We can say that our VCC, if we're looking at the loop, is equal to the voltage over the emitter part, right? Because there's going to be some voltage here. So we're going to have IE times our RE, and then we're going to have plus our voltage of the base emitter. And since it's a PNP, it's going to be like right here. So we'll do the voltage of our base emitter, and it's going to be the absolute value. So the absolute value of our VBE. And then you're going to have plus the voltage over this side as well, right? We want to add all these voltages together, and that will give us the total voltage that came in. That's going to be IB times our RBB. And then after this, we have to do plus the VBB, which is the voltage of this part right here. That's also important. Putting all of these together, we're going to want to rewrite this so that we can solve for our IE. Now, we have to rewrite our IB here, that way we can factor it out. And our IB, we can rewrite this and set it equal to. If we look at the notes again, we have a few things that we can do. The most nice one here would look to be our IC over beta, because we can rewrite our IC as alpha times our IE over beta, which we can just write as, if we cancel out the betas, IE over beta plus 1. So that's going to go inside of there. And now we can factor around everything and get everything to one side. If we do this, we're going to get that our IE is equal to, we're going to have our VCC minus our absolute value of our VBE minus our VBB as well. And this is all happening over the RE because of this right here. And then we have plus our RBB over our beta plus 1. And now we can plug in our values. We were given our VCC here as 11, our VBE is 0.7, our VBB we were not given. We need to find this. So that's what we're going to do next. But our RE is given as 2.3 kiloohms. And I guess another important note that RB, we mentioned this before, but RBB is equal to our RB1 in parallel with our RB2. So this is going to give us a value of approximately 13.88. And we can rewrite this out, but solve for our VBB. So IE is equal to, we are going to have 11 minus 0.7. Then we have another value, so we'll do minus. We need to find this value. Our RE, which is going to be 2.3 kiloohms. And then we have plus the 13.88 over, and this should also be in kiloohms as well. That looks correct. So this is going to be in kilo because our RB1 and RB2 are given to us in kiloohms, and this is going to be over 21. So now we need to solve for our VBB. That's going to be our step 4. So how do we do this? Well, let's use the voltage division. If we use voltage division and we look at our main circuit and our second circuit, we know that we are going to have, that's just common with voltage division. We have ground on both sides, and then we have a resistor on our output, resistor on top right here, and then we have our input. Our input voltage is obviously VCC. And our output voltage, well, if we look at this one right here, it's going to be our VBB. So we're going to write VBB here. Now our resistors are going to be RB2 and RB1. So that's how we would write that down. Now we need to solve this. So VBB is going to be equal to our VCC, which is the source multiplied by our resistor that is over, which is RB2 over RB2 plus RB1. And so we are going to plug in our values for the VBB. And this is going to give us that our VBB is approximately 7.13465 volts. We can now plug it back in here, 7.13465, and then we are going to get that our IE should equal to about 1.06903 milliamps. And then we can take this and then we can plug it back into here. So if we plug it back into here, and then we plug our beta values in, we're going to get that our IC should equal to 1.01812 milliamps. So that is the answer for this one as well. And now we can rewrite this in here, plugging our values in. So our RC is equal to, we're going to have 2, we're going to have our 1.01812 milliamps, and then we also need to solve for our VB now. So that is another thing that we're going to have to do. So solving for VB will be like our step 5. Previously in the last problem, our step 5 was to get our max and min, and that was for, again, this problem. However, when we look at our PNP, our max and min is just going to be the VB over 2. We talked about this right here. It's a little bit different in this wording than we had in this wording. And that allows us to, I guess you can say, skip a step. And so we can skip the other step that we did for the other one. So the similarity ends there. And then in our step 5, we want to find our VB. Well, our VB for our PNP is just going to be equal to the VBB plus our IB RBB for this circuit. Because we have the VBB right here. Oh, and I forgot to mention also, this is pretty important, that our VB should be right here. This is important because our VB is going to be equal to the, of course, the VBB going into it, and also the IB and RB over it. So that's similar to how we found it last time as well. So now we can plug in our values. VB is equal to 7.13 for 65 volts. We have plus our IB, and our IB we can find by putting our IE over the beta plus 1. That's what we did like right here. So that's what we did like right here. So we're going to have 1.06903 milliamps over our 20 plus 1, so that's going to give us a 21. And then we multiply this by our RBB, which we found to be 13.8 right here. And that is kiloohms. So 13.88 kilos. And the M and the kilo would just cancel out here. And then we are going to multiply these, add these all together, and then we are going to get that our VB is approximately 7.8412 volts. So that is going to be the value for that. Now for here, we would just plug it back into our top equation, so we have 7.8412 volts. And that means at the end of the day, this RC, if we plug it into a calculator, is going to be equal to 3.851 kiloohms. And that is going to be the answer to this problem and how we would go about solving it using the notes that we have.